I thought I'd talk about the joy, surprise, and excitement of soap operas. Okay, so previously on The Ancient and the Restless, Nikki tries to share a tender moment with Archimedes, but he breaks the social rules and, well, actually is her about the finite versus the infinite, and then computes the upper bound on the number of grains of sand that would fit in the universe. And what's interesting about this is that they had, the Greek numeral system had a myriad, which was 10 to the fourth, and they could go up to a myriad, and that's kind of as high as they would go, so 8-digit architecture. And so, I mean, 10 to the 63 kind of is well beyond that. So he, had to invent big numerals. And he published his results in a paper he called The Sand Reckoner. And that was really good. Then his rival across town, Catherine, was like, hey, I've got a big numeral system of my own. And, she has some plans for her big numeral system. And, he doesn't want to cede his big numeral fame. So he challenges her to count the number of cattle. There's 4 colors of cattle, and it's divided into bulls and cows. And he gives a bunch of proportions for the bulls. Like white bulls are 1/2 and 1/3 of the black together with the yellow, and etc. And then gives some proportions for the cows. Same sort of thing, white were 1/3 and 1/4 of the whole of the black, and so on and so on. And so Catherine gets to work, infinitely many solutions, because we got one free parameter, and she, does some stuff, and then she does some more stuff, and she's like, hey, the smallest number of cattle under the sun is 50 million, and you could take any multiple of this number, and it would also work. And Archimedes is impressed, but not that impressed, and tells her that, so he ups the ante and's like, hey, with the white and black bulls together, they form a square. And when the yellow and dappled bulls are together, they form a triangle. So, and Catherine's like, yeah, no big deal, how hard can it be? He's like, if you can do this, then I'll really be impressed. So Catherine knows about square numbers. She works some stuff out. She does some factoring. She gets a result about what k should be. She knows about triangular numbers. She does a few more things with the square number stuff, and she ends up figuring out, hey, all I need to do is find an integer solution to this equation where y is divisible by 4657, and that's kind of where she stops. Not really possible. So Archimedes is very pleased with himself, and the problem kind of goes away. So fast forward about 2,000 years to French mathematician Lagrange. These equations are now known as Pell equations, x squared minus dy squared, where d is some positive integer. And Lagrange proved that they have infinitely many solutions. And actually, much earlier than that, the Indians figured out how to do this. In 628, Brahmagupta figured out that if you have one solution, then you have infinitely many. And Bhaskara II had a method for producing that first solution. But the Europeans didn't know about the Indians' work, so they did it totally separately. Fermat, Wallis, Lord Bronkner, and then Lagrange came along and used continued fractions. So you might be wondering, why are they called Pell's equations? And it was just a mistake. But once things get named, they just stay. So yeah, what's a continued fraction? Continued fraction, you start with a number bigger than 1, you subtract the integer part, then you invert it so it's bigger than 1 again, and you rinse and repeat. So for square root 33, it might look like this. And a good fact about square roots is that there's a periodicity. You see that this bottom right one has the same result as the top right one, so this will just repeat indefinitely. 5, and then the 1, 2, 1, 10 will just keep going. These integer parts are sometimes called the quotients, and you can use the quotients to build rational approximations to the square root. So you take 5, 5, 1, 5, 1, 2, 5, 1, 2, 1, and you can build these approximations. They get closer and closer to the square root as you go. And really fascinating, at the end of the period, right before that last one, the convergent gives a solution to Pell's equation. So 23/4 translates to 23/4 being a solution to x squared minus 33y squared is 1. Then you take powers of that thing, and that gives you all the solutions. So once you find the first solution, you can just keep taking powers of this quadratic integer, and now you get all the solutions. Okay, fast forward another 100 years, and Amthor finds out about Archimedes' cattle problem, does all the same work, and is like, hey, it's just a Pell equation, and we know how to do that stuff now. So I'll just use continued fractions. And has a period of 92. So the last convergent in that list has this as the solution. But we need a y that's divisible by 4657, so we have to take the 23/29th power of this thing, which is, as you might guess, not computable by a human. But anyways, she has, this is the smallest solution. There's 206,000 digits, and the first 4 of them are 7766. All right, so then we fast forward to 1965, and University of Waterloo, they got this cool IBM 7040 with 32K of memory, and they decided to compute this thing. I know that's not as impressive as 434-bit modular arithmetic on a Commodore 64, but so they do this. It takes 7 hours and 49 minutes to compute. They published the first and last 50-digit numbers. There was a group also in 1889 that spent 4 years computing digits, like computed 30 digits at the front and 18 digits at the back. So that was a good project. Anyway, you might notice that the first 4 digits are 7760, so Amthor is mortified that, luckily she didn't try to compute more than 4 digits. That would have been rough. Then in 1981, they get this new Cray 1 computer, and they're like, hey, we got a new computer. Let's make sure that things are set up right by just solving Archimedes' cattle problem. Sure. So they compute the digits and do all the verification. It takes about 10 digits. And then this Harry Nelson guy is like, hey, it's never been published before, so might as well just publish like what the solution looks like on 47 pages where the digits are like 1/3 of actual size. So I thought we would maybe compute it right now. And I was really interested in doing it quickly, so I wrote my code in Ruby. So, don't look. Close your eyes, okay. Oh, that was close. I'm glad no one looked, thanks. So we got some continued fraction stuff. Not all that hard, pretty straightforward. And then we got to take powers of quadratic integers, which is also not all that difficult to do. So hard code in the solution to part 1 because I was too lazy to do that part. And the first solution, we just need to compute the continued fraction convergent. And then we got to take the 23/29th power of that thing. and multiply by those other values, and that's it. So we can print this thing off. Whoops, that's not what I meant to do. Whoops. So yeah, 0.01 seconds in Ruby on this wimpy laptop. Probably we should, I got like a minute left or something, so.
Seven 760268186486818269530232832832138866642.
Thanks.